part 2 of today's lesson, a little bit of a review. Cosecant x, cosecant is the reciprocal of sine. So cosecant x is 1 over sine x. Secant x is 1 over cosine x. Then the sine x over cosine x is tangent x. And cosine x over sine x is its reciprocal, cotangent x. Don't forget, when you multiply reciprocals, that result is 1. So sine x times cosine x is 1. Cosine x times secant x is 1. Tangent x times cotangent x is 1. Okay? Now, we have some Pythagorean identities. That's going to be the new piece in today's lesson. These are based on Pythagorean theorem. If we have a triangle in the coordinate plane, one leg sitting on the x-axis, theta in the corner at 0, 0, just like we did with exact values, the lengths are x, y, and r. So x squared plus y squared equals r squared. Okay, this point P, kind of traveled. This point P is x comma y. Okay, so that x coordinate is the length, that y coordinate is its height, and then r is the hypotenuse. So x squared plus y squared equals r squared is just Pythagorean theorem. If we divide by r squared, you see what we get in that second step. Then remember that x over r is the ratio for cosine. So x squared over r squared is cosine squared x. Y over r is the ratio for sine. So y squared over r squared is sine squared theta. And that's equal to 1. So this identity here becomes really, really important. Sine squared x plus cosine squared x is equal to 1. Now, you may need this solved for one function or the other. So if we needed sine squared x is 1 minus cosine squared x. Also, we can solve this for cosine squared x. Cosine squared x is 1 minus sine squared x. Okay, so these other rules come from that basic Pythagorean identity. Now, there are 2 other Pythagorean identities that come from this one. Okay, one of them involves dividing each term by cosine squared. You see the result here. So one of the other Pythagorean identities is tangent squared x plus 1 equal to secant squared x. Then there's a third one. If we divide the original by sine squared x, we get 1 plus cotangent squared x equaling cosecant squared x. If you're looking at these and you're thinking, I'm never going to be able to remember those, I have a solution for you. It's a hexagon, and it's magic. Okay, maybe not technically magic, but it's really, really, really helpful. Okay, so to help ourselves remember this, to help ourselves remember or figure out those Pythagorean identities and to remember some of the others, we draw them on a hexagon. Hexagon has 6 sides, and the further we go into this unit, the neater my hexagons will look, I promise. For now, bear with me. Okay, 6-sided figure, make the top and bottom horizontal. Okay, then we're going to put our trig functions around it. Actually, we're going to put a 1 in the middle. Put a 1 in the middle. We're going to use that in a minute, I swear. So on the hexagon, on the left, start with tangent x. We know that tangent x is equal to, we're going to go around the circle, around the hexagon, sine x over cosine x. That's how we're going to start the hexagon. Now, for the other pieces of the hexagon, we're going to use the reciprocals straight across. Tangent x, straight across. Its reciprocal is cotangent x. Sine x goes straight across. Its reciprocal is cosecant x. Cosine x goes straight across. Its reciprocal is secant x. Okay? Now, the beauty of this is it takes one fact to remember how to do this. Tangent x equals sine x over cosine x. Tangent x equals sine x over cosine x. Then you just need to know the reciprocals. Put the reciprocals straight across the hexagon from its original function. Okay? Now, the beauty of this is that the relationships work all the way around this hexagon. Meaning, we already talked about how sine tangent x was equal to sine x over cosine x. We remember, too, that cotangent x is equal to cosine x divided by sine x. That relationship works all the way around the hexagon. Okay? So, for example, sine x is equal to tangent x divided by secant x. Okay? We could also say that cosecant x is equal to secant x divided by tangent x. Okay? It works in either direction. Secant x, we'll start with secant. Secant x is equal to cosecant x divided by cotangent x. And around the circle in any direction, around the hexagon in any direction. Okay? Now, we started this to help you with the Pythagorean identities, the squared ones. Okay? The very first one we talked about was sine squared x plus cosine squared x equaling 1. Let me show you how this works. Sine squared x plus cosine squared x equals the 1. So that pattern makes the number 7. It's a little easier to see if you make that 7 big. Okay, so if we have this 7 in this little piece, okay, that sine squared x plus cosine squared x is equal to the 1. Now, one of the others was tangent squared x plus 1 equal to secant squared x. Tangent squared x plus 1 equals secant squared x. Again, it's along the number 7. So the other place this works is in a third piece of the hexagon. 1 plus cotangent squared x is equal to cosecant squared x. And those are your Pythagorean identities. So as you draw the hexagon with the top and bottom horizontal. Top and bottom are horizontal pieces, not slanted pieces. Okay? Any piece of the hexagon where you can naturally draw the number 7 makes a Pythagorean identity. A plus goes across the top of the 7. Equal sign goes down the side of the 7. Okay? And this is how you can remember those Pythagorean identities. Okay? As I work things in this unit, I have a hexagon labeled right next to me. There is one taped to my computer monitor right now. And it will stay there through this unit. Okay? So, those Pythagorean identities again. Sine squared x, this is the one that will come up most often. Sine squared x plus cosine squared x is equal to 1. Okay? The other one on the bottom left, tangent squared x plus 1 equal to secant squared x. And then the one on the bottom right, 1 plus cotangent squared x equal to cosecant squared x. Those are your 3 Pythagorean identities. Okay? Be aware, you can solve any of these for a different function. So in the second one, tangent squared x plus 1 is secant squared x. That could be solved for tangent squared x. Tangent squared x would equal secant squared x minus 1. Or cotangent squared. If we wanted cotangent squared x by itself, that would be cosecant squared x minus 1. So you can solve these with basic algebra and rearrange them. Be a good idea to practice labeling a hexagon. Will be a good idea to write that down several times. Okay, and I recommend you keep one next to you as you work these problems. I do it. I keep a hexagon next to me when I work these problems. So take a look at number 2. We are looking for what is not equivalent to cosine squared x. Not equivalent. Okay, if we look at these Pythagorean identities, if we look at A, okay, 1 minus sine squared x. If we get cosine squared x by itself, it is 1 minus sine squared x. Watch that order when you subtract. Okay, so A really does equal cosine squared x. It's out. Okay, then on B, cotangent x over secant x cosecant x. Yeah, I'm going to simplify B up here. Okay, cotangent x is cosine x over sine x. Then in that denominator, secant x is, let me go a little different, 1 over cosine x. Cosecant x is 1 over sine x. So to divide with fractions, leave that first one alone. Cosine x over sine x. Then multiply by the reciprocals in the denominator. So that would end up being multiplying by cosine x over 1 and multiplying by sine x over 1. So we have a sine x in the denominator, divide out with a sine x in the numerator, and that's equal to cosine squared x. So B does equal cosine squared x. It's not the answer choice we're looking for. Okay? In answer C, we have a subtraction in that numerator, cosecant x minus sine x, all over cosecant x. We can't divide out the cosecant x's here because of that minus sign. Okay, so we have cosecant x over cosecant x minus sine x over cosecant x. We're splitting that into 2 fractions. Both pieces are divided by cosecant x. Now, any value divided by itself is 1. So cosecant x over cosecant x is 1. Minus sine x over cosecant x. Those are reciprocals and we're dividing them. So that would be sine x times sine x being the reciprocal of cosecant. Okay, so that is 1 minus sine squared x, which is cosine squared x. So C is not the answer we're looking for. On part D, we have 1 over secant squared x. Okay, that's 1 over cosine squared x, which is cosine squared x. Secant is the reciprocal of cosine, so 1 over secant squared is cosine squared. So again, D is not equivalent. Okay, that leaves E as the correct answer, meaning it's not equivalent to cosine squared x. Now, it looks pretty similar. Okay, the identity is sine squared x plus cosine squared x equaling 1. So to get cosine squared x by itself, it would be 1, and then we subtract the sine squared x. So sine squared x minus 1 is the opposite positive negative signs from what we need. So answer E is actually equivalent to the negative of cosine squared x, not positive cosine squared x. Very similar. In example 3, we're going to be simplifying trig expressions and proving that they're equivalent. So if we look at 3a, we have that expression on the left, 1 plus cosine A times 1 minus cosine A. To work this out, double distribute. 1 times 1 is 1. 1 times minus cosine A is minus cosine A. Cosine A times 1 is plus cosine A. Then cosine A times minus cosine A, it's a negative. Cosine times cosine is cosine squared A. Then combine your like terms. Yeah, even though they're cosine A's, they're still like terms. So minus cosine A plus cosine A zeroes itself out. And we have 1 minus cosine squared A. Hopefully we're getting a little more used to that identity. That does equal sine squared A. If we look at the original identity, sine squared x plus cosine squared x equal to 1. Okay, if we have 1 minus cosine squared x, it moved that cosine to the other side, leaving us with sine squared A. So we showed through algebra and identities that that was equal to sine squared A. And that is what we needed to do. So looking at part B, we have cosine squared x minus sine squared x, not a plus. And we're transforming that into 1 minus 2 sine squared x. So the left side has a cosine and a sine. The right side only has sines. So I'm going to take this cosine squared x, write it as 1 minus sine squared x. Then there was still a minus sine squared x on that side. And now we're going to combine like terms. Minus sine squared x minus sine squared x is 1 minus 2 sine squared x. And this is what we were asked to prove was equivalent. Because the right-hand side of the original problem only had sines, no cosines, converted that cosine squared x into an expression with sine squared x. Now, looking at part C, we are multiplying this out. Remember, to square something, you are multiplying it by itself. So this is cosine m minus secant m times cosine m minus secant m. And again, we'll double distribute to multiply all that out. Cosine times cosine, cosine squared m. Cosine times minus secant, minus cosine m times secant m. Then minus secant m times cosine m, and then plus secant squared m. All we did there was double distribute. Okay? Now, if you notice right away, cosine and secant are reciprocals. So cosine squared m stays, minus 1, because cosine m times secant m is 1. Then minus another 1. Secant m times cosine m is again 1. Plus secant squared m. Okay. Now, Cosine squared m minus 1. Cosine squared m minus 1. We know from the identity sine squared x plus cosine squared x was 1. Cosine x minus 1 would mean we had sine x by itself, sine squared x, but that would equal, 1 minus cosine squared x. We have the opposite. We have a positive cosine squared x and a minus 1. So that's actually a negative sine squared x. Put a negative on the sine squared, put a negative on the 1, change the sign on the cosine squared, and we have a negative 1 plus a cosine squared x equaling that negative sine squared x. Then, on the other trig identity, we have a secant squared m and a minus 1. We have a secant squared m with a minus 1. I really like that to write right there. So, if we look at that hexagon for the secant squared m, I'm going to scroll back up to it. Here's our hexagon. Okay, that secant squared. Okay, we have, it's that second trig identity, that second Pythag identity. We have tangent squared x plus 1 equal to secant squared x. So that tangent squared x by itself would be secant squared x minus 1. If we look at our problem, we have a secant squared x and we have a minus 1. That is a tangent squared x. And I changed somewhere to m. Kind of surprised I waited that long in the problem to change them to x's. Okay. Now, this is one of the more challenging problems, but we do have tangent squared m minus sine squared m. Okay, we have it in a different order, but the positives and negatives match, so it's the same. Okay, so going back through this one, first thing we did was double distribute. Then secant times cosine is 1. So we had a minus 1 for each of the middle terms. In knowing I had to transform them into other trig functions, I didn't add those ones together. Okay, left those minus 1s in the problem. Okay, so looking at D, left the ones in the problem, then use the Pythagorean identities. If you're converting squared trig functions into different trig functions, look at those Pythagorean identities. Let that hexagon help you. So on part D, we're converting tangent x plus cotangent x into cosecant x times secant x. So we need to convert two expressions added into two expressions multiplied. So we need to be really careful about how we do that. We have tangent x plus cotangent x. I'm going to go to sines and cosines. So tangent x is sine x over cosine x plus cotangent x is cosine x over sine x. Okay? Now, we need to be able to add those together. In order to add those fractions, we need a common denominator. Denominators are cosine x and sine x. Those don't have anything in common. So we'll multiply that first fraction by sine x over sine x. We'll multiply that second fraction by cosine x over cosine x. Now we can add those fractions together. Okay, we have the same denominator. Sine x times sine x, sine squared x, plus cosine x times cosine x, cosine squared x, all over that common denominator of sine x times cosine x. And again, because we have that plus sign in the numerator, that ruins us from being able to simplify anything by dividing out, because that numerator is not multiplied, it's added. Okay, then we know that sine squared x plus cosine squared x is 1. So that's 1 over sine x times cosine x. Okay, we can think of that as two separate fractions now because that denominator is multiplied. 1 times sine x over 1 times cosine x. 1 over sine x times 1 over cosine x. Well, 1 over sine x is cosecant x, and 1 over cosine x is secant x, and that is exactly what we wanted to prove. So this is a little bit different from what we've been doing. This is more reasoning and simplifying than it is solving for an answer. Okay. Highly recommend that you know those top 5 identities on the top of the first page, the reciprocals and the tangent and cotangent rules. Also, learn how to draw that hexagon and label it. That will help you with those Pythagorean theorem-based identities there. All right, that's all for notes today.